Hello everyone and welcome to our session, which will be all about on how to tackle consistency related design challenges in distributed data intensive systems. And we are in particular approaching it with domain driven design, which is widely used in practice and also addresses one of the major challenges of data intensive systems, namely the complexity of data. Of course, this complexity also impacts the complexity of our domain models we need to build, and in the end also the complexity of the software we need to design and implement. And this is an area where domain-driven design quite shines, and domain-driven design is all about achieving one primary goal we always have in software engineering in general, namely the reduction of complexity. And regarding this, domain-driven design has one central concept. It is the concept of a bounded context, and what a bounded context basically says is that for every model your software is based on, this model should only be valid within clearly defined boundaries, and these boundaries also should manifest somehow. For example, usually a bounded context has its own code base and also its own database. If you are familiar with microservice architectures, then you probably know that one microservice usually corresponds to one bounded context. Now, I would like very shortly have a look into the architecture of a single bounded context. You typically have this three-layered architecture. The important thing is that your domain model, which is hosted in the domain layer, is clearly isolated from any technical code or application code residing in the infrastructure layer or the application layer. Also, I would like to point out that in these different layers, there are really different kinds of operations. For example, in the infrastructure layer, we have only these low-level read and write operations to update records in the database, whereas in the domain layer, we have semantically rich domain operations implementing our core business and domain logic. And this is in particular, or it's quite important in the light of a statement that Pat Helland made in 2009, when he actually said that it is time for us to move past the examination of eventual consistency in terms of updates and storage systems, and the real action comes when we start to examine it in the context of application-based operation semantics. Now, what we believe he basically means is that a lot of people examine eventual consistency only in the infrastructure layer, for example, in the database management system. And what we are in particular aiming at is to examine eventual consistency in the context of the domain layer. So why is this beneficial? It is because we can exploit the semantics of the domain in order to increase concurrency. And what we are in particular aiming at is to increase the number of domain operations that can run concurrently and conflict-free at different replication nodes. Right, and in order to motivate this a bit more, I would like to really shortly recap how relational database management systems typically handle concurrency control. Now, you probably know that the databases continuously monitor those low-level read and write operations. They also consider so-called conflict relations between those low-level read and write operations, and they use it to build a conflict graph. And you all know that if this conflict graph doesn't have any cycles, it means that the corresponding concurrent execution of transactions is actually equivalent to a serial execution, and this in turn means that there cannot have been by any means any concurrency anomalies. Right, so the schedule given on this slide obviously does have a cycle in the conflict graph. So this concurrent execution of transactions would not be possible with serializable transactions. Now the interesting thing is, if we now look into the domain layer and see what actually happened in the domain layer when we executed this concurrent execution. Right, so here is the schedule again, and as you can see on the domain layer, 4 domain operations have been executed: withdraw and deposit operations on a banking account. And as you all know, withdraw and deposit are commutative operations, and in addition they have been executed atomically here. So this basically means that from the viewpoint of the domain layer, from the viewpoint of domain semantics, nothing bad has happened. This concurrent execution could have taken place without doing any harm to your data. But it's not possible with serializable transactions, and this issue has already been addressed by multi-level transactions. Multi-level transactions exploit semantics of operations and consider level-specific conflict relations that reflect the compatibility of operations. And of course, the overall goal is to increase concurrency. Now, what you typically have are 3 levels. At the top, there are transactions, followed by business operations, and at the bottom, in the infrastructure layer, there are low-level read and write operations. Now, regarding compatibility relations, they remain the same at the infrastructure layer. At the domain layer, non-commutative operations are considered to be conflicting. Now, having all of this, if at each level then the corresponding conflict graph is acyclic, then what we get in total is called so-called multi-level serializability. And the really cool thing is that multi-level serializability is in practice quite comparable to what serializability does bring. Right, so if we had multi-level transactions, this concurrent execution would have been possible, which is actually a good thing. And we like the idea of multi-level transactions and pick up their idea of considering compatibility relations at the domain layer in terms of domain operations. Now, what we are in particular investigating are compatibility relations that go beyond commutativity. And why is that? Basically, if you're confronted with real-world domain logic, you will see that in most of the cases it is rather not trivial to come up with a commutative design of your domain operations, because real-world domain logic is quite complex. And this is why we try to find alternative ways of thinking compatibility, and for that we distinguish in particular different types of operations. And one important type are incremental operations. Now, incremental operations, they read first and then write, because they first need to evaluate the current state of the data they intend to update in order to derive the updated value. So counter increments would be a popular example. List append operations are another one. Please note that the append operation is not commutative. However, if two append operations are executed concurrently at two replication nodes and are later propagated and re-executed at the other replicas, we will at least not have a lost update. It's simply a matter of the ordering of the last two elements. And if we in addition have a infrastructure that guarantees that all operations will eventually be executed in the same order at each replica, we will also get convergence without the possibility of a lost update. The second important class or type of operations are blind updates. Is somewhat the opposite concept of an incremental update. The interesting part of blind updates is that by definition of the lost update phenomenon, you can exclude the occurrence of lost updates with true blind updates. So true blind updates are not able to produce a lost update by definition. Right, so we hope we could give you an idea of our proposed compatibility relation. We cannot go more into the details because of the timing constraints. If you like our research, please have a look into our paper. We also sketch our reconciliation algorithm there and show how we can guarantee the eventual absence of lost updates. I would also like to highlight that this is only a small part of an overall engineering approach that we are currently developing. Next to the semantic compatibility of domain operations, we also provide guidelines to come up with an optimized design of your domain objects in order to reduce the overall chance for conflicts from happening in the first place. You can find all our guidelines on GitHub for free. Please also have a look into our scientific papers and note that we are also currently developing a programming framework supporting our guidelines. So thank you very much for your attention. Do not hesitate to contact us and thanks for your attention.